Hi, I'm Aaron Johnson, a PhD student in the Department of Aeronautics and Astronautics here at MIT. And it's about 2 o'clock in the morning. We're in the library, but we're not working on homework, we're not working on a project. We're actually proving that the Earth is rotating around on its axis. How are we doing that? It's no light task, I know. We're using a 160-year-old device called a Foucault Pendulum that we built here this evening. So we'll show you how we built it, how it works, and like I said, prove that the Earth really is spinning around. And so, in the words of Foucault himself, you are invited to come see the Earth turn. So everyone else is off getting ready for our demonstration, but how exactly is this going to work? I mean, how can a Foucault's pendulum show that the Earth is rotating around on its axis? Let's take a look.
A pendulum is composed of two parts. There's a long string, or wire in our case, with a bob at the end, a heavy weight. When you start it swinging, a pendulum swings back and forth until acted upon by an outside force. This is called inertia. A Foucault's pendulum, if left for a long time, will appear to precess or rotate. So if we look at the pendulum from a top view, it starts swinging like this, and then in the northern hemisphere, after time, it will appear like this. After more time still, like this. It's appearing to precess clockwise in the northern hemisphere. It's opposite in the southern hemisphere. So what if we have a pendulum at the north or south pole? This spot, the Earth is twisting, and that includes the pendulum building. But the pendulum doesn't actually move. So while the pendulum appears to rotate to an observer in the building, it's actually the building turning while the pendulum stays in the same position. The pendulum precession period is 24 hours. What if the pendulum is at the equator? This spot on Earth isn't twisting, but it's traveling eastward on Earth's surface. Here, the pendulum won't precess at all. So these are the two limiting cases, but what about in between? At this spot on Earth, there is twisting and traveling eastward. The pendulum will show this twisting motion, but not the traveling component of the motion. As a result, the precession period will be greater than 24 hours. There's a simple formula that lets us find the angular velocity of our pendulum, represented by omega, in degrees per day. Omega is equal to 360 times the sine of the latitude. Here in Boston, our latitude is 42.36 degrees north. So, this gives us an angular velocity of 242.56 degrees per day. This tells us that our pendulum will precess 10.1 degrees every hour. This is called the Coriolis Effect. Looking from the top down, pendulums in the northern hemisphere precess clockwise, while pendulums in the southern hemisphere precess counterclockwise. This has effects on Earth that we can see every day. Take hurricanes and typhoons, for example. If we have little bits of wind in the northern hemisphere rotating clockwise, we're going to get an overall rotation that's counterclockwise. So, hurricanes and typhoons in the northern hemisphere rotate counterclockwise. In the southern hemisphere, the opposite is true. Hurricanes and typhoons rotate clockwise.
Many people think that the Coriolis effect also causes the water in your toilet bowl to rotate counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. It's not really true. The Coriolis effects are there, but they're so small that they're really overwhelmed by other factors, such as which way the jets in the toilet are pointing and how the bowl was filled. So it's unfortunately not true. When we start our Foucault's pendulum, we need to make sure not to put any sideways motion on it. Otherwise, we're going to see that motion and not the rotation of the Earth. So, we're going to start our pendulum the traditional way.
We got the pendulum swinging, but it's going to take a while for there to be any visible precession. So, let's skip ahead 1 hour. In 1 hour, the pendulum has precessed about 10 degrees, but we can also see that its amplitude is smaller than before. This is due to damping. We used a heavy bob and a long wire to reduce the effects of damping, but you can never completely eliminate them. Foucault's pendulums that you see in science museums have an electromagnet that gives the wire a kick each swing and keeps the pendulum swinging. There's also a bit of sideways oscillation in the pendulum. You can see it traces out a narrow ellipse. This is likely because the wire is made of many smaller wires twisted together, and when it's under tension it tends to untwist a bit. This introduces a sideways torque leading to the elliptical motion. However, we can still clearly see the precession of the pendulum, and thus the rotation of the Earth.
Well, I say with that experiment, we proved that the Earth really is rotating around on its axis, which is what we hope to discover. So I guess that's good. Not bad for a night's work, but I really think I'm gonna head out and get some sleep now.